So, hello and welcome to our webinar about dilatometry, more than just the determination of thermal expansion. My name is Doreen Rupp and I'm working for more than 8 years now here in the applications laboratory in ZELP in the field of dilatometry and thermomechanical analysis. So during the next around 30 minutes, I will give you an overview about the possibilities you have using a dilatometer or a TMA. Before we start, just a comment regarding the webinar software. At the end of my talk, you will have the possibility to ask some questions, so please use here the chat window of the webinar toolbar. We start with a short introduction into NEDG. So what is NEDG? NEDG is a group company with 3 business units: analyzing and testing, grinding and dispersing, pumps and systems, and on top we have our holding. NEDG was founded in 1873 by Thomas and Christian NEDG here in ZELP, and we have a turnover around 475 million. In the fiscal year 2015-16, and meanwhile we have more than 3,500 people working for NEDG worldwide, and you find us in around 35 countries at the moment. I'm working in the business unit analyzing and testing, and we are offering products and services for the applications from low to high temperature fields, so from minus 260 degrees C up to 2800 degrees C. And here we have products for thermal analysis, so the determination of changes in dimension and mass, and also phase transition and enthalpies as a function of temperature. Then we are offering products in the field of thermophysical properties. So here for the determination of thermal conductivity, specific heat and thermal expansion coefficient, and on the third part in adiabatic calorimetry. And I think we are also well known for our service for contract measurements, seminars, trainings and meetings and so on. But now we will go on with the topic of today. We start with a short look into the definition of thermomechanical analysis. So what is TMA? This is a technique in which the deformation of a substance under a non-oscillatory load is measured as a function of temperature or time, while the substance is subjected to controlled temperature program in a specified atmosphere. So this is the definition which you can find in ASTM A473. And you get also there more information about the load, which may be compressive, tensile, flexural, or torsional. So if you apply a load to the sample which is very small, so that you do not cause any deformation of the sample, then the mode is called thermodilatometry. So the difference between these two techniques is that for TMA you apply a non-oscillatory load, and for dilatometry you measure the dimension of a substance under a negligible load. As a result, you receive the temperature-dependent length change. So usually you start at room temperature, measure the initial sample length, and then you heat up your sample or cool down your sample and determine the length at a certain temperature T. And this is subtracted from each other, so you have the temperature-dependent length change. To make results more comparable for samples with different length, usually this delta L is divided by the initial length of the sample L0, so that you have the relative length change. With these results, you can go on and calculate the coefficient of linear thermal expansion, and here we have 2 different values. One is the mean coefficient of linear thermal expansion, and the other one is the differential coefficient of linear thermal expansion. So here you can see the calculations for the 2 values, but I think more visible, or it's better to understand if you have a look at this slide here. So Here we have the length change versus temperature, and in black here we have our expansion curve. So the differential expansion coefficient alpha is the slope in a point on the expansion curve, like depicted here. So it's the slope of a tangent at some point t, whereas the mean coefficient of thermal expansion is the slope in the temperature range delta t. So here we have the slope of a secant between 2 points on the expansion curve. Here you see the broad range of applications which you can apply for a dilatometer. So yeah, we already discussed linear thermal expansion and the coefficient of thermal expansion, but in addition you can also get information about phase transition temperatures, sintering temperatures, shrinkage steps, glass transition temperatures, dilatometric softening points, volumetric expansion, decomposition temperature, and using additional software you can also get information about caloric effects, density changes, and sintering kinetics. And we will start now with phase transition temperatures. As a first example, I have here the measurement of a polymer sample. It was a natural rubber sample. It was measured in a temperature range between -120 up to room temperature, and in blue you see here the expansion curve, and around -62 degrees C you see a change in the slope of the expansion curve, and this is where you find the glass transition of the polymer. So the glass transition is the change in a polymer from hard and brittle state into a softened or rubber-like state. The method that is mainly used to determine the glass transition of polymers is DSC. DSC is the abbreviation for differential scanning calorimetry, and so here you see the comparison of the results. In red we have the DSC curve, and in blue the expansion curve, and as you can see here the results are very similar. But I also have to say this is not a must. So here we are applying two different techniques. In the DSC you have a sample in a crucible on a sensor, and you heat it up and you have a look on caloric effects inside the sample, whereas with the dilatometer or the TMA you apply a load to the sample and you measure the mechanical properties. So the values do not have to be the same. They might differ slightly. As a next example, I have here the measurement of a steel sample. So in blue, you see the thermal expansion, and in red, the coefficient of thermal expansion, and in this case, it's the mean coefficient of thermal expansion. And what you see here between 740 degrees C and 760 degrees C is a step in the expansion curve due to the alpha-gamma transition inside the steel sample. So here in addition, I also have to add something regarding phase transitions. Phase transitions you can only see in an expansion curve if you have a change in the volume of the elementary cell of a crystal or whatever of a material. If this is not the case, you will also not see something in the expansion curve. The next example shows the measurement of an SiO2 sample. So in black here we have the thermal expansion, and in red the temperature curve. So we heat up the sample, keep it isothermal for a certain time, and then cool back to room temperature. In the beginning you see an expansion up to a maximum at around 1120 degrees C, and then we have an intended deformation of the sample, and during this part here we have the formation of a new phase. And so during the cooling you see a new step in the expansion curve between 211 and 196 degrees C, and if you heat up the sample a second time, you see this step already in the beginning of the measurement. So here during this phase here we have the formation of a new phase, and in this case it's cristobolite. And what you see here as the jump in the expansion curve is transformation from alpha cristobolite to beta cristobolite. So far about phase transition temperatures. We go on now with density changes. As an example, I show you here the melting of a cast iron sample. In black, we see the thermal expansion, and in red, the mean coefficient of thermal expansion. So for the measurement, as we go into the molten range, we cannot put the sample without any container or something like this in the sample holder. So we use these containers, which consist of a cylinder with 2 pistons, and in between here we have our sample. And then we heat it up, and what you see here in the beginning is the expansion of the solid sample. And then we have here the so-called mushy zone where melting of the sample takes place. And here above 1370 degrees C, we have the expansion of the melt. So using this expansion data and the density at room temperature, you then can calculate the density change versus temperature. And this is what is depicted here in blue. So the density is calculated here with the assumption that with the assumption that the expansion is isotropic in all directions, and also with the assumption that there is no mass loss during the measurement. So, and here below you can see the sample container subsequent to the measurement, and also this was the sample afterwards. Where are these data used? For example, for the optimization of casting processes. Here an important parameter is the thermal conductivity, and for the calculation of the thermal conductivity you need the density, the specific heat, and the thermal diffusivity, and all parameters in dependence of the temperature. So as we have seen now, we can calculate the density versus temperature using the expansion data. You get the values for the specific heat using a DSC, and the values for the thermal diffusivity using an LFA, so a laser flash analysis. We will go on now with caloric effects. Also in this case we need an additional software tool which is called CDTA, which stands for Calculated Differential Thermal Analysis. So what is done here? In black, you see the temperature program. So this is the temperature increase as it is programmed during preparation of the measurement. And we have in red the real temperature curve during the sample run. And due to phase changes which occur in the sample, we have a slight deviation between the two temperature curves. And this is what is evaluated then as the CDTA signal. And as an example, I show you here the quartz transition with CDTA evaluation. So in black we have the expansion curve, in red the first derivative of the expansion curve, and in blue the CDTA signal. So already here in the expansion curve you see a change in the slope, and here with a maximum in the first derivative at around 584 degrees C, and also with a maximum at 584 degrees C in the CDTA curve. So this is the quartz transition from alpha to beta quartz inside the sample. As a next example, a more complex example, I have here the measurement, the sintering of a clay sample. So in black we see the thermal expansion, and in blue the CDTA curve. So as you see here, we have here some additional effects in the CDTA result. So in the beginning here as a small endothermic peak, we have the dehydration. So here water, adsorbed water and interlayer water is released. Then we have a small exothermic effect around 330 degrees C. So here we have the burnout of organics. Then we have a huge endothermic effect around with a maximum at 590 degrees C, which is the dehydration of the clay. And then here at the end of the measurement, we have a small exothermic effect, which is a phase transition in this case. So with using CDTA, you can get also additional information about endothermal and exothermal effects inside your sample. So our next topic is the sintering kinetics. Here you see the sintering of an alumina sample. So in black we have again the thermal expansion, in blue the first derivative of the expansion curve, which is also called the sintering rate, and in red we have the temperature increase. So what you see here, sintering starts around 1380 degrees C, and between beginning and end of the isothermal step here we have a shrinkage around 15%. So there's a special feature available called rate controlled sintering, or short RCS. Here the output of the measuring system is used to modify the temperature program. So usually measurements are performed with a constant heating rate, but in this case the heating rate is variable to keep the sintering rate, so the first derivative of the expansion, at a constant value. If you have a look at the next slide, I think it's more clear what is meant here. So in black we have again the expansion curve, in red the temperature increase, and here we have our sintering rate, so the first derivative of the expansion curve. And here you give a threshold value. In this case it was 0.1% per minute. So this value is kept constant over this period here, and as you see the heating rate is adapted to keep this value constant. Here this is the so-called start-stop mode, and there's another mode available called ISO mode. Here you give two threshold values, an upper and a lower, and here the sintering rate should be between 0.1% per minute and 0.2% per minute, and here also the heating rate is adapted to keep the sintering rate in between these two values. Let us now compare the results. So here you see in black again the measurement with a constant heating rate, so the sintering rate is variable, and in red we have the measurement with constant sintering rate between 0.1 and 0.2% per minute, so the so-called ISO mode, and in blue we have the measurement with a constant sintering rate of 0.1% per minute, so-called start-stop mode. What you can see here is at the end you receive a higher shrinkage level using RCS, so a higher densification of the sample. But if you have a look at the time scale here, you also see that RCS measurements last longer in comparison to measurements with a constant heating rate. So what is the aim or the goal of sintering studies? So the goal is to find a sintering temperature or a temperature program where you have a high densification, but at the end you also want to save time and by this also energy costs. So in this case the ISO mode gives a higher densification of the sample and saves time in comparison to the start-stop mode. There's another approach to sintering optimization, and this is the kinetic analysis. So here on the first step you perform several measurements, you export the data and go to the net thermokinetic software and perform an analysis so that you find a model that describes the sintering curves you have measured before. And using this model you can then go on and make some predictions, optimizations or simulations. So one way is to have a temperature program and you measure the signal like DSC or dilatometer, thermal expansion, or the other way is you have, for example here, a more complex temperature program. you use thermokinetics, and then you can calculate the measuring signal. Or the other way around is you know how your sintering should take place with at which sintering rate. If you now have no RCS available, you can could perform several measurements to adapt this sintering rate, or you go to the thermokinetics and then you get the temperature program for any constant rates of change. As an example, I have here the measurement of Aragonite, which is a natural occurring mineral, as you can see here. Sorry. So in the first step, we have here the measurement at 10 Kelvin per minute. And in black, you see here the thermal expansion, and in red, the sintering rate. So sintering starts around 990 degrees C. And between the maximum here and the end of the heating, we have a sintering step of around 22%. And what you see here in the sintering rate is that we have here two minima. So we have two sintering steps here. In addition, you perform measurements with heating rates of 20 Kelvin per minute and 5 Kelvin per minute. And what you see here in a comparison is that the lower the heating rate, the earlier the sintering starts. And on the other hand, the lower the heating rate, the higher the densification of the sample. With this data, you then go to the thermokinetic software, and here you find the model which describes the reaction inside your sample. So in this case, we have a three-step reaction from A to B to C to D, but of course there are other types available. And what you see here is the calculated and the measured values fit very well. So we have also here, a very high correlation coefficient. And using this model, then you can go on and predict the length change for example, for different isothermal temperatures. So if you have a look here at 700 degrees C, there's almost nothing happen. If you get back to the measured curves here, you see we are here at 700 degrees C, so there could nothing happen up to there, this temperature. So you can go on and can calculate the length change for other isothermal temperatures. Or you can predict, or you can make predictions for a freely selected temperature program, like for example shown here, for heating from room temperature up to 1000 degrees C at 1 Kelvin per minute, and an additional and subsequent isothermal step of 600 minutes. So the measurement would take about 27 hours. With thermokinetics, you can calculate this. If you have the model already, you can calculate this within a few minutes. Or you can make predictions for a much more complex temperature program, for example, like shown here, with several isothermal steps and different heating rates in between. So up to now, we had a look on on the different application fields using the result of the expansion measurement and using also additional software, but there's also the option to couple the devices, for example, to evolve gas analysis like mass spectrometer or FTIR, and the TMA you can also couple to a humidity generator to study the expansion under defined humidity. And with the next slides, I will show you some examples for these two parts here. So we start with evolved gas analysis. So in this case, we have a measurement of the TMA coupled to a mass spectrometer. So in green here, we see the thermal expansion. In blue, we have mass 18 for water. And in purple, we have mass 44 for carbon dioxide. So in the beginning here, where you see several small steps in the expansion curve, you see here in the curve for M18, for mass 18, small peaks, which refer to the dehydration of the sample. So here you find a release of adsorbed and interlayer water. Then we see here a peak around 350 degrees C and mass 44, where we see almost nothing here in the expansion curve. So this is due to the burnout of organic material inside the sample. And then we have a huge peak in the curve for mass 18, which is due to the dehydroxylation of the clay sample. So using the coupling to a mass spectrometer, you get additional information about your sample, but usually, or let's say like this, it's not a very common combination, TMA and gas analysis, or also dilatometer and gas analysis, because usually you have to destroy something to see something in the mass spectrometer, and this is something which you usually do not do in the dilatometer as well as in the TMA. So this combination, this coupling is more common, for example, for a TG or an STA. As a next example, I show you the expansion of a human hair at defined humidity. So in red we have here the change in relative humidity, and in green we have the expansion of the human hair. And as you can see, the hair follows the different the changes in the relative humidity, and this is something which is also commercially available in a so-called hair hygrometer, but in this case it's not a human hair inside. In this case it's a hair from a horse tail. And as a last example, we measured also wood samples under defined humidity. Wood is used as a construction material for different applications. And if you have a look on wood, you see that it's quite anisotropic. So therefore we prepared samples in different directions. So we measured one sample which was prepared perpendicular to the annual rings, one sample tangential to the annual rings, and one sample in length direction. And we measured the samples at 20 degrees C and 50% relative humidity. And what you see here is the expansion of the wood sample is quite anisotropic, quite different here. So the lowest expansion you see here in length direction, whereas you see a really high expansion in tangential direction. So this is also the reason why wood changes its shape in different humidity. So now I would like to show you the devices that were used for the measurements. So one is the dilatometer VO2 Expedis, which is available in 3 versions, Classic, Select, and Supreme. So the device you see here is the dilatometer VO2 Expedis Supreme. And with this device you can measure samples with a length up to 50 millimeter and a digital resolution of 0.1 nanometer in a measuring range of plus minus 25 millimeter. You can apply forces between 10 millinewton up to 3 Newton, and we can cover a temperature range here between minus 180 up to 2000 degrees C. And what we have here in this device is a force-controlled measuring cell. So in this case we control the force during the entire measurement and keep it constant. On the other side we have our TMA VO2 Hyperion, which is available in 2 versions, F1 and F3. Here you can measure samples with a length up to 30 millimeters and with a digital resolution of 0.125 nanometers. The measuring range is smaller in comparison to the dilatometer, so here we have plus minus 2.5 millimeter available, and the force range is between 1 millinewton up to 3 Newton. And here we can cover a temperature range between minus 150 to 1550 degrees C. So as a short summary, you see again the slide which we have seen now several times during this talk. So what can we do with a dilatometer or a TMA? So we can first of all measure the linear thermal expansion. But in addition, we get information about phase transition temperatures, sintering temperatures, or for example also caloric effects, density changes, or using additional options like shown before. You can also, for example, study the expansion of materials at different relative humidity. With this, I would like to say thank you for your attention, and now we have time for your questions. There's a question regarding measuring under defined relative humidity. So in this case, you would need a TMA. Coupling to the dilatometer is not possible. In this case, you need a TMA, thermomechanical analysis, and here as you want to measure a human hair, you need the tension mode in this case. One question regarding the purge gas. Yeah, maybe you recognized in many slides, helium was used as a purge gas. So the choice of purge gas depends on the measuring range, on the temperature range, as well on the sample itself. So we use mainly helium because helium has the best thermal conductivity in comparison to other gases except hydrogen, but hydrogen is something which you do not want to use in your lab. So therefore we use helium, especially for low temperature ranges. So if you want to go down to minus 180 or minus 150 degrees C, then it's better to use helium in this case, but of course you can use also other purge gases like nitrogen or argon. You have to be careful with nitrogen because I know some metal samples might react with nitrogen, and also at higher temperatures, if you go up to 2000 degrees C, for example, you can have the formation of cyanides due to the graphite atmosphere that you usually have in this temperature range. There's a question regarding which alpha value is the correct one to compare samples. So I think this depends what you want to know. If you want to see the expansion between two different points without taking into account what happens in between, then you compare the mean coefficient of thermal expansion. And I think this is also what is done in many cases, that you compare the mean coefficient of thermal expansion. If you need the expansion coefficient at one temperature point, then you need the differential coefficient of thermal expansion. One question regarding sintering studies. So using RCS. So I cannot say that isomode is the best for all samples, because in our case we got better results using isomode in comparison to start-stop mode, but this might be also different for other materials. So here you usually start using performing a first measurement with a constant heating rate to get an information about the sintering rate and the maximum sintering rate, and then you can go on and testing with ISO mode and also with start-stop mode. There was one question I already received in advance. So it was about the difference between dilatometer and TMA regarding the measurement of polymers. So which is the suitable technique here? So the TMA is the method which is mainly used in polymer applications. So here you can apply very small forces to your sample in comparison to the dilatometer. And you also have here other modes available like penetration or 3-point bending or also tension mode. So usually I would go in the direction of TMA, but for some applications, for example, if you have samples with really low expansion like fiber reinforced polymers, then it might be better to go to the dilatometer, where you can measure larger samples, and in this case also with a higher resolution. There's a question regarding the difference between DTA and DSC. So DTA means differential thermal analysis, and DSC means differential scanning calorimetry. So with DTA you can get information about endo and exothermal effects inside your sample. And as far as I know, with DSC you can also quantify these effects. So if there are no further questions, I would like to say thank you for your attention. And if you have further questions, you can use the email address which you see here, and I will answer them afterwards. So goodbye and have a nice day.